Okay, so your final exam is a big deal. You only get one shot to kind of prove what you know, no retakes, and it's going to influence your grade tremendously. So you have got to have good notes. Make sure, in fact, if you don't even want to write on this packet, you can get out a sheet of notebook paper, copy these problems down into your notebook paper, kind of like we had on our solution packet for the test I handed out. Work them out step by step by step. Take lots of space, make it clean, neat, and you can use your notes for the final. Then I'll just come around and look and give you credit for your review if you've got way good notes. So, I think that's it. Here we go. Okay, so the study of complex numbers. So all these numbers are complex. There's two categories. There's reals, there's imaginaries, and a bunch of subsets beneath each of those. Okay, so let's start with the imaginaries. Imaginaries are pretty easy to recognize. They will be followed with an I, or they will have a negative under the square root. And the first one's pretty easy to identify they're imaginary. This one's not so much. So if you ever have a negative under the square root, that is the red flag. That's an imaginary number. So this is really imaginary square root 5. If we've got the square root negative 16, take the negative out, that is 4 imaginaries. And if we have like a negative 2, square root negative 8, take the negative out, that's going to be negative 2 imaginaries, square root 8. And then you could break down 8 even further. 8 is not a perfect square, but it's got a square in it. 8 is 4 times 2. 4 is 2 times 2, and there's your square. So you've got negative 2 imaginaries, and it's a square root, and you've got 3 2's in there, so you got a cube. So square roots undo squares. There is a square living in that cube with 1 left over, so that means 1 2 comes out, 1 2 stays in. I've already got on the outside a negative 2i, so you times it, so it's going to be negative 4i, and on the inside a square root of 2. So if it has an I, it is super easy to identify that it's imaginary. If not, it's going to have a negative under the square root. Now if it's something like this, if it's 2 plus square root negative 16, this is of the form a plus bi. So a plus bi, there are two terms, two parts. The a is the real part, and the bi is the imaginary. So if I've got 2 plus negative 16, that's really 2 plus 4i. Okay, it's not purely imaginary, so it cannot fit in the imaginary. Half of it's imaginary. The 4 is imaginary, but it's got a part that's real. So you cannot say that it lives in the reals. You cannot say it lives in the imaginaries. This is just straight up complex. And complex is always going to be of the form a plus bi. Put your real first, imaginary second. Okay, so now the reals. We spent the first half of the quarter going over your reals. There's two classifications for reals. It is either rational or irrational. Irrational, these are decimals that go forever with no pattern. You cannot write it as a fraction. And they are most of the radicals. So square root 2. If you try to change that to a decimal, it goes forever. Even if your calculator only shows the first 10 or so digits, that's 1.414213, blah 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 blah. So these are non-terminating, so they never stop decimals. And they are non-repeating. There's no pattern decimals. So their decimals go forever. Okay, now the other half, rational. These can be decimals, like 1/2, but that is 0.5. They terminate, they stop. or 1/3. That's 0.3333 forever, or they've got a pattern. So these decimals are nice. So the rationals, we've got like 4 different sets here. Rationals include everything under them. They include integers, they include wholes, they include naturals. So if it is rational, it includes all those sets. So the very first set, the naturals, that's just 1, 2, 3 to infinity. The wholes, that's 0, 1, 2 to infinity. The integers introduce the negatives. So dot dot dot, negative 2, negative 1, 0, 1, 2, and then natural, or rational, I mean, they include the numbers in between, these fractions. So rational is anything that can be written as a fraction. So these decimals that either terminate or they repeat with a pattern. So we've got 5 numbers here. Let's classify them, tell me which set they belong to, and then plot them on a complex number plane. So a complex number plane, your x-axis is going to be the real number line, and then your vertical one is going to be the imaginary number line. So this first one right here, 3 minus square root of negative 9. Okay, now that's a red flag. That is imaginary. So this is 3 subtract I square root 9. And square root 9 is a perfect square. So this is really 3 minus 3i. Okay, now it is of the form a plus bi. It has a real part and it's got an imaginary part. So can't say that it's all real and can't say that it's all imaginary. So this is only going to be found in the complex number set. So to graph it, the real part I go over 3, 1, 2, 3, and then I go down 3 imaginaries, 1, 2, 3, and there it is right there. Okay, I'm going to erase every time so I don't get too cluttered. Okay, the next one, square root. Okay, so this is another red flag. That's imaginary. Take that out, and you're going to have imaginary square root 28. 28 is not a perfect square. So if I type in square root 28 on my calculator, that is approximately, so that's what these squiggles mean, it's approximately, I'm going to round it, it's 5.2915026 blah 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 imaginaries. So this is purely imaginary. There's no real part with it. This is a straight up imaginary number, and it's like 5 1/4. So I'm going to go up 1, 2, 3, 4, 5, a little bit past 5. That is where you can find that number. The next one, negative 3 square root of 15. Okay, the negative's on the outside, so I'm okay. It's some real number. There's no imaginary stuff going on. 15, there's nothing you can pull out of 15. A 3 and a 5, those are both prime. So I don't have any squares. So on your calculator, if you type in negative 3 times the square root of 15, that is a number approximately negative 11.61895-ish. So it's real, 100% real. Negative 11. Oh, I forgot to classify these last two. Okay, here we go. So let me plot this one first, and then we'll classify them. So negative 11.6 is somewhere over here. There's negative 11. There's negative 12. It's between the negative 11 and negative 12. Right there. Okay, now this one. This is classified irrational. It's an awful decimal, goes forever. It is real, and it is also complex. And this one was imaginary and complex. So it lives in those two sets of numbers. Okay, fourth one down. We got 2i over I. and that behaves just like 2x over x, or 2 times 5 over 5. So you got the same thing on top and bottom, and anything divided itself is just 1. So 5 divides 5 leaves you with 2, x divides x leaves you with 2, I divides I leaves you with 2. So it is 2. Okay, now 2 shows up in every single group except for imaginary and irrational. So 2 starts out here. Starts out at the bottom and works its way up. It is natural. It's whole. You can find it in the integers. You can find it in the rationals. You can find it in the reals. You can find it in complex. So it lives in 6 sets. You gotta have them all. Natural, whole, integer, rational, real, complex. And 2 is just right there on the real number line. Okay, last one, -2/9. -2/9. If we type that on the calculator, we get -0.22222. So the decimal that goes forever, but there's a pattern, so it's rational. So this shows up first in the rationals. That is the very first time decimals show up. So no decimals in the naturals, no decimals in the wholes, no decimals in the integers. That's the first time decimals show up. And it's one of 2 decimals. It's either going to be clean and neat or ugly and nasty, which is the irrational. So because we're clean and neat, we're going to go rational, real, complex. That's how we're going to classify it. Rational, real, complex. Then to plot it, -0.2 is almost a quarter, so it's negative between 0 and 1, somewhere right there. Okay, let's look at these. So we're given 3 conjectures. Here's what we got to do. We got 3 choices. Either choose between always, sometimes, and never. And you have to have 3 examples that show why your conjecture is true, or just 1 to prove that it's not. So if you're going to go with always, you've got to have at least 3. If you have a sometimes or never, you just need 1. And you need the one that shows that it's sometimes or never. So here we go. The sum of 2 rational numbers is always, sometimes, or never rational. So if we're adding any of the rationals, so we can choose any of the naturals, wholes, integers, or fractions. Okay, so it's always. Because if you add 1/2 plus 1/2, that's 1, but that's still rational. 0 is a lot of times the one we're going to use to prove them false. 0 plus a -4, that's a -4. Any rational you choose and add, it will stay rational, and that is the same. Add and subtract are the same. So those are going to be both always, because we could do 1/2 plus a -1/2, and that is the same thing as 1/2 subtract 1/2. So this one's an addition, you could say, and this one's a subtract. So either adding a negative, or you could subtract a positive. It's the exact same thing. It doesn't matter. They're both going to give you the same answer. Okay, the product of 2 rationals. If you times 2 rationals, so I'm not giving all 3 examples, I'm just giving a couple. So if you multiply 2 rationals, so pick any rational. If you do 1/2 times 3, that creates 3 halves, which is rational. And -4 times 0 is 0, that's rational. It is going to be always. Okay, the quotient. This one is tricky. So division. If you divide any 2 rationals, it is a sometimes. 'Cause if you pick this rational, 8 divided by 0, that is undefined. You can never, ever, ever divide by 0. So this 8 is irrational, 0 is irrational, but the answer, that is not rational. So when you divide two rationals, it does not always create a rational. If we do the reciprocal, 0 divided by 8, that creates a 0. Or you could do 2 divided by 5, and that creates 0.4. So those are all good, all good. This is the only instance that you're going to run into trouble if you ever try to divide by 0. Okay, number 2. The sum of two irrationals is sometimes irrational. So if I look at like square root 2 plus square root 2, that is irrational, that is irrational. The answer is 2 square roots of 2, which is also irrational. But if I look at the square root of 2 plus a negative square root of 2, that creates 0, and 0 is rational. There's no decimal, nothing. That's a sweet number, nothing funky about 0. So that is irrational, but the answer is nice. Getting the difference, the same thing. I could go square root 2 subtract square root 2, and that is, this one above is add, this one is subtract, same thing. So it is also a sometimes. The product of two irrationals, sometimes. If I take square root 2, which is a crappy decimal, and times it by itself, anytime you take an irrational and times it by itself, square root 2 times square root 2, or any of these radicals, it will create a perfect square. Square root 4, and square root 4 is 2. And 2 is rational. That is a nice number. Okay, the last one, same with divide. The quotient. So you could do this. You could use this for an example. Square root 2 divided by 0. Well, no, you can't, because you need to use two irrational numbers. And that one is irrational, but that one is rational, so you can't use that example. But you can use this. You can do square root 2 divided by itself, square root 2. And square root 2 divided by square root 2 is just 1. So if you divide anything by itself, it creates a 1, and 1 is a nice rational number. So 2, they were all sometimes. 3, okay, now we're going to just focus on the imaginaries. If you add two imaginaries, will the answer always, sometimes, or never be imaginary? We're going to go sometimes. So if you add like 2 imaginaries plus 3 imaginaries, that creates 5 imaginaries. But again, it's 0 is the one we're trying to kind of focus on. So if I had 2 imaginaries plus a negative 2 imaginaries, that would create 0, and 0 is not imaginary, 0 is real. So the difference, that's going to be the same thing, because I could write 2 imaginaries, subtract 2 imaginaries, that's 0, 0 is real. The product of 2 imaginaries, that's a sometimes, because if I have I times I, an imaginary times an imaginary creates a real. But if I had like 2 imaginaries, gosh, this might be, I wonder if we could put never here. The only thing is if we allow you to use this. No, this is a dang good question. So the product of, you can only use 2, they have to be imaginary. It is never going to be imaginary. It is always, if you ever have an imaginary times an imaginary, it will always spit out a real. So if we had like 2i times 3i, 2 times 3, that's 6, I times I is a negative, and that's a real. So as long as you're limited to 2 imaginaries and multiplication, the outcome, the product will always be imaginary. So this is the first never we've seen. That's a good one. Okay, last one, the quotient of 2 imaginaries will never be imaginary. So if you have 2 imaginaries divided by 3 imaginaries, imaginary divided by imaginary, that is just 2/3, and 2/3 is real, it's rational. God, the only question I have is this. What if you, I don't know about 0. I don't think 0 imaginaries is just 0. It's nothing. So there's kind of no such thing as 0 imaginaries. So if you have 0 imaginaries, it's real. 0 is just always going to be real. Okay, so I was wondering, but if you did like this, 2 imaginaries divided by 0 imaginaries, and then the imaginary divided by imaginary, so now you're left with 2 divided by 0, which is undefined. But 0 imaginaries, that is not really an imaginary. So if you ever divide 2 imaginaries, just like if you times 2 imaginaries, they turn real. So any 2 imaginaries, if I have square root 5 imaginaries divided by 6 imaginaries, imaginary is going to divide imaginaries, and you're going to be left with this real number. Okay, now, so for the test, I think you're just going to have a calculator. We'll do plus, minus, times, divide. It will not do imaginaries for you, so you have to know how to add, subtract, times, divide imaginaries on your own without the use of a calculator. So these problems come from your quiz. They look intimidating, but they're not bad at all. All you need to remember is if you have I times I, an imaginary times an imaginary, that's a negative. So move number 1, let's multiply, distribute the 3 imaginaries to both of these terms. So 3 imaginary, make it look nice and neat, times 10 is going to be 30 imaginaries. Then I just put a plus. 3 imaginaries times a negative 6 imaginaries is going to be 3 times a negative 6 is negative 18. And then I times I is a negative. So it's going to turn that. Negatives turn negatives positive. They turn positives negative. Okay, now I'm just going to copy and paste 7 minus 3i subtract. Okay, this right here, that is an imaginary. So take the negative out, and it is I. And you got square root of 16, and square root of 16 is a negative 4i. Okay, so let me copy all this. 30i plus 18 plus 7 minus 3i minus 4i. Okay, now you got 5 terms. And put it in a plus bi form. Put the real first and the imaginary second. So those are imaginary, those are imaginary, those are imaginary. If you total those, if you got 30 imaginaries minus 3 minus 4, you have a total of 23 imaginaries. And if you total your reals, your 18 and your 7, you've got 25. So your answer in box number 1, you should put a 25. In box number 2, since the I is following it, I only need to put 23. Okay, let's look at this guy right here. Okay, now rule number 1. This is a big deal. If you had like a 2x squared versus 2 plus x squared. We call the first one a monomial, and we call the second one a binomial. Okay, a monomial only has one term. Binomial has two terms. It's got a number, and then it's got a letter. So if you have a monomial, so 2x squared, if you expand it, it is really 2x times 2x. And if we multiply that, that gives us 4. 2 times 2 is 4x times x is x squared. So if you have a monomial, you can take the exponent to both of those, and that could be 2 squared x squared. If you have a binomial and you do that, you're going to get a wrong answer. So if you take that exponent to the 2, that's going to give you 2 squared, and if you take that to the x, that's going to give you an x squared. So it's going to be like 4 plus x squared, but that is incorrect. That is wrong. You cannot distribute the exponent unless it is all one piece, unless it's a monomial. So always expand it. So let's take 2 plus x squared and expand it. So that's going to be 2 plus x times 2 plus x. Now you got to distribute the 2 to the 2 is a 4. 2 to the x is a 2x. Then x to the 2 is a 2x. And x to the x is x squared. Now if we add up these, we have an x squared. 2x and 2x, that will give me 4x and 4. So this is what the answer should be if you just took the exponent to both those terms. You got 2/3 of it. We got the 4 and we got the x squared, but we did not get the middle 2 x's. So don't ever distribute an exponent. Just expand it, work it out, and you'll never ever miss it. So this first one, here we go. You've got 1 plus I squared. So expand it. 1 plus I times 1 plus I. Divide that by I cubed. Okay, so I'm going to start distributing. 1 times 1 is 1. 1 times I is I. I times 1 is another I times I is a real, and that is a negative. And on bottom I got I cubed, so that's like I. That is a negative. Okay, now on top, my positive 1 and negative 1, that's gone. And my I plus I, that's 2I. And on bottom, that I is a negative 1 times I, and you've got I divided by I, and that is 1. So I've got a negative 2. That's kind of a good problem. Okay, let's do this guy right here. So here and here is multiplication. So I've got to go 2 times negative 3. That is a negative 6. 2 times 2I. That is 4I. I times a negative 3 is negative 3I. And I times 2I. In front of here is just a 1. So 1 times 2 is 2. I times I is a negative. So let's make that negative. Okay, now between this part and this part, I'm going to think of this as a negative with the 5i, so I'm going to go plus negative 5i times 2 plus negative I. So between these two quantities is addition, it is not times. We're just going to add these up. So let me total this mess up. So if I got 4i minus 3i, 4 minus 3 is just 1i. And I've got negative 6 and negative 2, so that's a negative 8. So my reals are at negative 8. I just have one imaginary. And if I distribute this negative 5i to the 2, That's negative 10i, negative 5i to the negative I. So in front of here is just like a negative 1. So negative 5 times negative 1 is a positive 5. But I times I is a negative. Okay, so now my reals are negative 8 and negative 5. So that's a negative 13. And my imaginaries are 1 and a negative 10. So that's a negative 9 imaginaries. And that's your answer. Okay, now this one, you need to kind of work through each of them. And of the 5, there's really only one that's going to take some time. So work through them all. Check all the ones that give you a 4i when you're done. So this first one, you have to take that negative to both of those. So it's going to be 3 plus 2i subtract 3 subtract 2i. 3 subtract 3 is 0. 2i subtract 2i is 0. So it's not that one. So that one only took 2 seconds. Okay, 2i squared times I cubed. 2i squared, 2i expanded, 2i. 2 times 2 is 4. I times I is negative. Then you need to times it by I. Okay, I is negative, so you got negative 4 times negative 1 times I. Negative 4 times negative 1 is positive 4i. So that one, yes. Okay, this one's the same as number 1. It's not going to take any time. 2 plus 2i. Take the negative to both of them, and it's going to, there's already a negative. It's going to be negative, negative, so it's going to be positive 2i. So 2 minus 2 is 0. 2i plus 2i is 4i. Yes, that one is a check also. Times 2 times 2 is 4. 2 times I is 2i. That one is a no. Last one. 1 times 2 is 2. 1 times 2i is 2i. I times 2 is another 2i. And I times 2. So there's a 1. 1 times 2 is 2. I times I is a negative. So this negative 2 and this 2 are 0. And 2i and 2i is 4i. And that one's a yes.